Okay, first of all, thank you for giving me this opportunity of the talk, and thank you for organizing this nice workshop. I'm Murai, a postdoc in Tohoku University, and today I will talk about this title and about the axion dark matter of two axions with mixing in the stochastic axion scenario. This talk is based on a collaboration with Fuminobu Takahashi and Wen In. They have already talked in this workshop. Okay, first I review the QCD axion. As we know, QCD axion is a solution to the strong CP problem and the Nam-Goldstone boson arising from the PQ symmetry. And importantly, QCD axion acquires a potential from the coupling to gluon like this. And here, chi is the scale of the potential, and it depends on the temperature. At high temperature, it is suppressed by temperature of this power, and at low temperature, it becomes constant. And by fixing the decay constant Fa, we can obtain the axion mass depending on temperature. And if the QCD axion oscillates around the minimum point of this potential, QCD axion becomes a candidate of dark matter. And in this talk, I will focus on pre-inflationary PQ breaking scenario. In other words, we focus on the homogeneous axion field value. And in this case, in the standard scenario, the dark matter abundance is explained by the misalignment mechanism. In this mechanism, the scale of the axion potential is determined by chi, and the oscillation timing is determined by the balance of the Hubble parameter and the mass. So if we have large decay constant, the mass becomes smaller and the timing of the oscillation is delayed. As a result, we obtain larger abundance for larger decay constant. And then if we have a typical initial field value of order of Fa decay constant, then we can explain the all dark matter with the decay constant of order of 10 to 20th giga electron volt. And if the decay constant is larger than that value, we require fine-tuning of the initial condition of field value around the minimum point of the potential. And this upper bound of the decay constant can be relaxed by considering the stochastic scenario. In this scenario, we consider low-scale inflation. And the Hubble parameter during inflation is smaller than the QCD temperature. Then the QCD potential is present during inflation. So the field value A is suppressed by the this gradient of the potential. And but during inflation, we have quantum fluctuation. So by considering the balance between the classical force and the quantum fluctuation, we can estimate the typical variance of the axion field value during inflation. And this can be understood from the Fokker-Planck equation. Here, P is the probability distribution of the axion field value, and N is the e-folding number during inflation. This term represents the classical force from the potential gradient, and this term represents the quantum fluctuation determined by the Hubble parameter. And this equation have the static solution like this. And from this exponential, we can estimate the typical variance of the axion field value. And we can confirm the previous estimate in the previous slide. And this distribution is called Bunch-Davis distribution. So if the QCD potential exists during inflation, we can realize the small initial field value dynamically. As a result, we can allow the large decay constant for low-scale inflation or the stochastic scenario. Here, note that this scenario requires very long inflation to realize this saturated distribution. And this scenario is free from the ice curvature perturbation constraints because we consider the low-scale inflation. Okay, and so far I have discussed the QCD axion. And we can also consider many axion-like particles coming from, for example, the Axiverse. And in the string Axiverse, the decay constant of the axion-like particles are typically string scale. And since they are much larger than 10 to 20 SGD or so, the axion-like particles with the misalignment mechanism is suffered from the overabundance. And this is called modular problem. And again, this overabundance can be solved by considering low-scale inflation. So the stochastic scenario can be applied to the axion-like particle as well as the QCD axion. And in this talk, I considered mixing if there is two axions and they mix with each other. Then for some parameter region, we can see non-trivial behavior. This is the main topic of this talk. Okay, this is, we consider two axions, A and phi, and this is the Lagrangian we consider. Here, A is the combination of the axion-like particle fields that couple to the QCD. So the QCD potential can be written like this using only A, and we consider another potential, V mix. And V mix have A and phi. So through this potential, the two axion field mixes. And here we assume that the scale of V mix is constant for all time. Okay. And here I show the sketch of the potential we consider. This QCD potential depends only on A, so it has potential in this horizontal direction, and it's flat in this phi direction. And here we call this direction capital phi, and then this V mix has potential in this capital phi direction, and the other direction V mix is flat. And here, what is important is chi is temperature dependent. Okay, and now we consider the stochastic scenario. And in the stochastic scenario, the axions, the field value of axions are suppressed by the potential, and we only consider around the potential minimum. So here we can approximate the potential with the quadratic one, like this. And here is the mass matrix. And due to this mixing term, this mass matrix is not diagonalized. And so we can diagonalize this matrix by using some rotation matrix. And we have mass eigenstates, and we call them SH, heavier mode, and SL, lighter mode. And this plot shows the mass eigenvalue depending on the mass ratio MA and M phi. MA is here and M phi is here. And at low temperature, chi T goes to the constant value and MA becomes large. So if in that case, the VQCD is dominant, the mass eigenstate is mainly determined by VQCD. And then the heavier mode is almost A, and the other direction phi becomes a lighter mode. On the other hand, at high temperature, chi vanishes, and the mass eigenstate is determined by this V mix. And then the heavier mode is this direction, capital phi, and the other direction A becomes a lighter mode. And here, where MA and M phi becomes comparable, here the avoiding level crossing take place. And the heavier mode always remains to be heavier mode. Okay. And next, we consider the initial condition determined during inflation. And here we consider the Bunch-Davis distribution. And Bunch-Davis distribution can be applied to the mass eigenstates. And so we can estimate the typical field value of variance of the mass eigenstates in the during inflation. And here we consider low-scale inflation, and so during the inflation we consider chi equal chi zero. And here we use subscript 0, representing using the chi zero. And their variance is written like this, and here heavier mass and lighter mass. So the Bunch-Davis distribution spreads in the lighter direction more. And to determine the initial condition for the consideration, we parameterize the initial condition by CH and CL coefficient. And these coefficients are typically of order unity. And by rotating again, we obtain the initial condition parameterized by CH and CL. Okay, and this is a sketch of the initial Bunch-Davis distribution in two limits. One limit is the case where MA is much larger than M phi. In this case, the VQCD is dominant and A direction is suppressed by the QCD mass. And the distribution spreads in the other direction phi. And the other limit is the case where M phi is much larger than MA. In this case, the mass eigenstate is capital phi and capital A. And in the heavier direction, the distribution is suppressed and spread in the other direction. But in the latter case, phi is the mass eigenstate during inflation. And even after inflation, independently of the temperature, phi remains the mass eigenstate. So in this case, we have no interesting dynamics, just obtain trivial dynamics. So we focus on this case. During inflation, the VQCD is dominant. And next, we consider the dynamics after inflation. And if the axions to axion fields move only after the QCD temperature, then the time dependence of the QCD potential means nothing. So even in this case, we have no interesting dynamics. So to see some interesting phenomenon, we consider that the axion starts to move on the potential at higher temperature than the TQCD. In other words, we are mainly interested in this parameter region. At low temperature, VQCD is larger than the V mix, and the field starts to oscillate before TQCD. Okay, and this is the sketch of the dynamics in this interesting case. First, during inflation, the initial condition is determined by the Bunch-Davis distribution. And here, red cross is the typical initial condition. And during inflation, VQCD is dominant. So the distribution is spread in phi direction. So typically, as the initial condition, initial value of phi is much larger than initial value of A, like this. Oh, sorry. And then after inflation, when the hyperparameter becomes comparable to the M phi, at that time, this is larger than MA, as I mentioned before. And so V mix determines the motion of the axion field. And so the field rolls in this capital phi direction, green arrow. And after then, the VQCD grows as the temperature decreases, and the mass eigenstate again becomes small a and small phi. Then the field starts to oscillate in this horizontal direction. As a result, we obtain the oscillation in the A direction with much larger amplitude than the initial condition. So we obtain the enhanced abundance of A through this dynamics. Okay. And to see this enhancement effect quantitatively, we numerically simulated the axion dynamics. For simplicity, we assume an equal to 1, actually this can be absorbed into the F phi. And since we are interested in the similar values of the decay constant for A and phi, we set they are same as simplification. And the initial condition is determined by the typical value with the coefficient of unity. And since we are considering the dynamics around the potential minimum, the initial value, the scale of initial value or the Hubble parameter of inflation does not change the behavior of the axions qualitatively, just proportional to F-inf squared, H-inf squared. And the remaining parameters are F and M phi, and we simulated for various values of them. And to see the enhancement and for comparison, we also simulated this system without mixing or n equals 0. Okay, here's the result. This is the parameter we used, and this is the case for the interesting dynamics. And as I sketched, first it has the large phi value compared to A, and it moves in the capital phi direction. And then around here, the VQCD grows and the oscillation changes the direction, and this A direction goes to the A direction. And as comparison, I also show the trivial case. First, if M phi is much larger than the maximum value of the MA, then the mass eigenstate is always capital phi and capital A. So the field first oscillates in the capital phi direction, and independently, the capital A direction oscillates. So we can divide the dynamics into two mass eigenstates, and this is a trivial case. And the other trivial case is where the axion starts to oscillate after TQCD. In this case, the mass eigenstate is effectively always small a and small phi, and the oscillation can be separated into two components. Okay, so we are interested in this non-trivial case. And here I show the time evolution of the energy density in the non-trivial case. The x-axis is the time normalized by the m phi, and the horizontal axis is the energy density for some component. Here, the solid lines show the energy density for the case with mixing, and the gray is the total energy density, and orange and green the heavier mode and lighter mode. And here we can see the heavier mode has larger energy density than the lighter mode. And as comparison, the dashed lines show the energy density without mixing. For red for A and blue for phi. And here, so the dominant mode A can be compared to this red dashed line. And here we see very large enhancements of the energy density of A. And here I show the enhancement factor for the different value of M phi and F. And for each line corresponds to different value of F. And the horizontal, vertical axis is the ratio of the energy density between the case with mixing and without mixing. And for each line, we have a peak. And here, and around the peak, we have three gray vertical lines. On these lines, this condition is satisfied. This means that the M phi and MA becomes comparable to the Hubble parameter at the same time. In other words, VQCD and Vmix becomes relevant at the same time. In that case, the non-trivial dynamics like this can be realized, and we obtain a large enhancement factor. And for smaller f, we obtain, for example, 100 times larger energy density compared to the case without mixing. And here we see some oscillatory behavior depending on M phi. And this can be understood as the oscillation in phi. Here, in this case corresponds to the maximal enhancement, this peak. And in this case, the phi direction does not oscillate, just roll into the minimum and then change its motion, direction of motion. But for larger M phi, it can oscillate on this phi direction. And this oscillation can be this oscillation is reflected to the oscillation in this enhancement factor plot. Okay, next, yes. Question?
No, just say 5 minutes.
Okay, thank you. Okay, next I show the energy fraction of the each mode. Here, the horizontal axis, vertical axis is same, the enhancement factor, and the blue line is the same as in the previous slide. And yellow and blue shows the energy density of heavier mode and lighter mode. And here we can see that the heavier mode is dominant, where the enhancement is significant. On the other hand, where the enhancement does not take place, the lighter mode becomes dominant. This is same as in the standard misalignment mechanism. Lighter mode remains later without oscillation. So lighter mode becomes dominant in this region. Okay, and this is the plot for the Hubble parameter during inflation to explain the all dark matter. Horizontal axis is M phi, and we fix the value of F. And above this gray line, the Hubble parameter is large, and we cannot use the stochastic scenario because the Bunch-Davies distribution can go over the cosine potential. So we focus on below this gray shaded region. And the blue and red line shows the Hubble parameter to explain the dark matter with only one axion field for axion-like particle, temperature-independent potential, and QCD potential. And with the enhancement of the axion energy density, we can account for dark matter with smaller H-inf compared to blue and red case. Okay, and finally, I show the how the enhancement is general for the some initial condition. Here, I parameterize the initial condition with an angle beta in the plane of CH and CL, the initial condition. And so for typical value of beta, we see the enhancement. Here, we fix M, phi, and F on this point. And on the other hand, with a tuned initial condition around here, here corresponds to very small beta. And in this case, the initial condition have a small phi value compared to A. And then it oscillates in the capital phi direction and oscillates in A direction. So the oscillatory amplitude becomes smaller than the initial condition, and the abundance is suppressed. But this is very rare case. So typically we see the enhancement for the once we fix the mass and decay constant of the axions. Okay, this is a summary slide. We have studied the axion dynamics with mixing in the stochastic scenario. And due to the temperature dependence of the VQCD, the mass eigenstates change in time. During inflation, it's QCD axion, the other. But after inflation, the VQCD vanishes, and this green direction becomes the mass eigenstate. And as a result, we see non-trivial dynamics like this. And as a result, we find the enhanced abundance of the QCD axion. So considering that we have many axion-like particles in widespread mass spectrum, there might be some axion-like particle in this mass region. Then always the QCD axion is enhanced and become dominant. In this sense, we say the QCD axion is the unique player in the title of the paper and this talk. But for some mass region, we have the mixed component of the heavier mode and lighter mode, or two axions. Okay, that's all. Thank you for listening.